We saw in the last video that when dealing with straight chain alkanes that we can get free rotation around the single bond, and I'll re-show you the example we used of ethane having free rotation about this single bond, causing its hydrogens to rotate along the circumference of this carbon. So the next logical step we should ask ourselves is, how do these conformations due to free rotation around single bonds manifest themselves in cyclic compounds? And we got to remember that there's a fundamental difference between straight chain compounds and cyclic compounds, and I'm going to show you that difference right now. This is how we draw the compound for cyclohexane. This hexagon, this hexagonal shape represents at each point a carbon, and you can count 1, 2, 3, 4, 5, 6 carbons, and each one of these carbons, like I've shown you before, has 2 hydrogens attached to it, one here and one here, and so each carbon does indeed have 4 bonds, but the hydrogens are implied. Since, and you can observe this for yourself, each carbon on this molecule, each point on this molecule is attached to 2 other carbons, then the free rotation about the single bond is no longer possible, because you don't have any point on this molecule where one carbon is attached to only one other carbon. When dealing with straight chain alkanes, whether it be ethane or butane or propane or whatever, you always have, for example, one terminal carbon. So if we draw, I don't know, propane with 1, 2, 3 carbons, you have a terminal carbon here and a terminal carbon here, and both of these terminal carbons basically have free rotation about this single bond. But on this cyclohexane molecule, we can observe that each carbon is attached to one. If we take carbon number 4 as our reference, each carbon is attached to one carbon to the left of it and one carbon to the right of it. So how does that fact change the conformational analysis of cyclic compounds such as cyclohexane? Well, in order to know that, we have to start viewing this molecule in 3D space from different viewpoints and perspectives. Right now, we're looking at this molecule in only 2 dimensions. We're basically looking at it from the top view in 2 dimensions. If we were to look at this molecule in 3D, we would see a much different molecule, and the reasoning for that is because although every hexagon and cyclohexane does take this geometry or does incorporate this geometry into its final form in 3D space, since each hexagon just naturally has a 120-degree inner bond angle for any one of these angles here, since hexagons like to have that geometry, and since each of these represent a carbon that does want to express the tetrahedral 109.5 degree geometry, what we see when we look at this molecule in 3D space is more of a hybrid of a hexagonal geometry and the tetrahedral geometry that each carbon wants to express. It was actually thought that the molecule resembles something like this, which in organic chemistry we call a benzene ring, which differs from a cyclohexane ring, and I'll explain why later. But as of right now, just pretend that this would be how cyclohexane would look in 3D space. What is wrong with this picture? Well, we have the hexagonal 120-degree angles here from this bond to this bond, and this bond to this bond, and so on and so forth. But what we aren't showing is that even though these carbons are bonded each to one other carbon, if we label this as carbon number 1 and then carbon number 2 and then carbon number 3, we see that carbon number 1 does have a bond to carbon number 2 and carbon number 3. And that fact does indeed restrict carbon number 1's ability to take the shape that it wants to, namely the tetrahedral geometry that we talked about in earlier videos. But it doesn't suppress it completely. And so this carbon number 1, can move up, or it can move down, or it can kind of wiggle about and express itself as closely as possible to the preferred tetrahedral geometry. So even though cyclohexane does in fact take a hexagonal arrangement when looking at it from the top view, if you're actually looking at it in 3D space, you're going to see that carbon number 2 for example, is going to start to kind of move over a little bit up higher, and this hydrogen is going to move a little bit down and to the, what is it, the right a little bit, so that we can get the textbook geometry of the tetrahedral molecule as closely as possible. I mean, it won't be exact, but they are going to try to take that arrangement. So we can look at it kind of as a mixture of both hexagonal geometry when looking at it from the top view, and tetrahedral geometry for each individual carbon that is going to be trying to express that geometry as much as possible. If we show you how the cyclohexane molecule actually is shaped in 3D space, it will look something like this. Okay? And this is from the side view, where each carbon has indeed tried to express its tetrahedral proclivities as strongly as possible. We're gonna move to a 3D view so that I can show you in more detail exactly what I'm talking about. Now, this is the top view of a cyclohexane molecule. This is what it looks like if you were looking at it directly overhead. But I'm going to rotate this molecule, and we do see the hexagonal shape. We see these 6 carbons forming a hexagon with their hydrogens kind of jutting out on each respective carbon. I'm going to now rotate this so that we're seeing it in 3D shape, and then you'll be able to see what I'm talking about when I say that it's kind of a hexagon on the top view, but when we move it, it takes tetrahedral geometries as strongly as it possibly can. So here we are starting to rotate this molecule, and we're going to start to see the tetrahedral shape appear. Alright, and this, now you can see that each carbon has kind of taken this tetrahedral geometry as strongly as possible. And this is what we call the chair conformation of cyclohexane, and it's the most stable conformation of cyclohexane, where each bond angle is as close to 109.5 degrees as possible, and they're actually at 111 degrees in the cyclohexane chair conformation, which is pretty close to the optimal geometry that each carbon wants to take. And so this is the most stable conformation of cyclohexane, and there's another chair conformation that is simply the inverse of this chair conformation, and a whole bunch of intermediaries between those two appear. Molecules are always moving about and are in perpetual motion, and since these, as we've seen before, since every carbon on a cyclohexane molecule is bonded to 2 other carbons, it can't freely rotate, like I said before, but it can move in ways that we call ring flipping. Cyclohexanes exhibit this phenomenon called ring flipping, in which, if we're looking at this leftmost cyclohexane chair, where each of the red hydrogens are pointing either up or down,